So what Dan just told you is that we have a very solid spec and we have to change it very, very slowly. And our goal in JDK7 was to make a solid spec for JSR 292 that we could then work under the covers and improve performance in JDK8 and following. And that's pretty much what we did. I'm going to tell you some of the refactoring adventures behind the curtain in the hotspot implementation. I expect this will be of deep interest to some of you and perhaps only academic interest to the rest, but I hope to make it an interesting case study in optimization and refactoring. The other thing that might be useful about this is that although it's hotspot specific, I've made an attempt to do something that serves much better than JDK7 as a reference implementation for JSR 292 for method handles and invokedynamic. The hope is that other VM implementers out there might be able to use some of these ideas, and we might even be able to common up some structure, which Dan, I promised I would think about, and so this is the trip report from thinking about that. So let's start. First of all, you have to realize that none of what I'm saying counts to the accountants. Okay, so what's good in JDK7? Well, the method handles are pretty powerful, and they can emulate just about anything you can do with bytecode. So it gives you a new way to get to the JVM's powerful software composition mechanisms. You can't do loop directly, right? But you can make your own loop combinators. And you can't do all cases of the invoke special of super from within a subclass. So that's a hole in the spec, which I don't know how to fix. The optimization of these guys is aggressive, and we get some good performance for many interesting benchmarks and many interesting applications in JDK7. The important tactic that works well in JDK7 is that when you have a constant method handle and you are compiling a call to it, the inliner goes to town on it, and the method handle graph structure is collapsed into machine code. So that's good. The caveat is it only works when the compiler can find a constant method handle. It does not work for, say, a non-constant method handle in the style of calling maybe a Lambda expression, if anyone cares about that. So yeah, there's a known problem which we're fixing in 8 for some reason. Let's see. So the thing that happens when you call a non-constant method handle is you go off what our users affectionately call the performance cliff. And this also happens when you scale up to a graph of method handles that is so big that the inliner says, I'm not going to inline all of that. I don't care how much you put on my plate. I'm only going to eat part of it. So that causes at the inlining boundary non-constant method handle invocations to occur, which are slow for reasons I'll get into later. Also, the generic invoke, as opposed to invokeExact, is slow because it well, I'll just confess it. It performs an as type on almost every call, which means that it recomputes itself. There's some caching in there, but it's pretty weak. Also, we found out that when users started building complex, say, Smalltalk or Ruby applications, this mysterious no-class def found error would come at unpredictable times. And so we found what we think is the cause of that, and it's related to some of the implementation decisions we made in 7 that we have revisited and changed in 8. The basic problem is that bytecodes contain call sites which we call nominal. A nominal call site is one which is specified with a symbolic reference. For those of you who are up to speed on the JVM reference manual and know exactly how the specification works, you'll recall that there's something called a symbolic reference in a get field or an invoke static or something like that. The symbolic reference gives a name of the method that you're calling. This doesn't mix well with function pointers. Function pointers don't always have names, and so when you go back and try and render function pointers into bytecodes, which we do internally, there are some difficulties. So we want a non-nominal way of crunching on and optimizing method handles. In fact, the root problem, I think, is that the JSR 292 implementation in Hotspot grew up along with the prototyping of at least 3 major versions of the JSR 292 specification. So what we thought we were building when we cut the first code turned out to be different by the time we were done with JDK 7. So there's a lot of architectural decisions in there that it wasn't the right time to revisit in JDK 7. The real problem in JDK 7 was to get a functional, a usable spec and a functional implementation of that spec. So here we are. Now it's time to revisit it, and based on the solid, fixed, final nth version design of JSR 292, we've picked a better internal representation. The original representation was built for flexibility of prototyping, I suppose. Each method handle had its own little piece of assembly language, and the assembly language was whatever was convenient to write as a sort of a mini interpreter for doing argument transforms on the interpreter stack. And so if we had to swap 2 arguments, it was fairly easy to write a little assembly language routine of a few lines to swap 2 arguments and then parameterize it and build all these things that are called adapter method handles in JDK 7. Each one, they're put in chains, and each one will do one transform. A transform might be a cast or a box or an unbox, something like that. It's all defined in terms of the interpreter stack. Therefore, when you try and compile these little things, the compiler looks at these jumps to assembly code and says, I'm not compiling assembly code for you, sorry. There's no intermediate language here I can process. Unless you can hand me something I know, like bytecodes, I'm not going to optimize it. And so in many cases, you fell off the cliff and you went into the interpreter, shuffling arguments on the interpreter stack. One way to look at this problem is that the JVM is too entangled with method handle semantics. It has too many little tiny connections to overly small operations like swap 2 arguments or cast 1 argument. Also, because of the assembly language interconnection, every method handle creation requires a JNI call for the VM to decide what assembly language stub he gets. Java is not given the assembly language to work with directly. Here's an example of when you win, when you get away from the assembly code, the way you win is you take, as I said, a constant method handle and then you render it to bytecodes. This happens transparently when the compiler is trying to compile a constant method handle. This is not something that the JDK knows about. It's internal to the JVM. This is only in JDK 7. What it'll do is it'll take something like this combination. Filter return value is the version of the circle operation from mathematics. It composes 2 functions. And so the composition of 2 method handles can be compiled to bytecodes fairly simply. In fact, all the noise of composition and building method handle graph structure eventually cooks down to maybe 4 bytecodes, which are listed there. And I've purposely chosen an unlikely mix of arguments and return values just so you can track which is which. We'll revisit this example much later. Now there are problems with this. You have to use a class loader that can see both A and B. Can you smell trouble coming? As soon as I say class loader, you should head for the doors. All right. So these are nominal calls. A nominal call is evaluated relative to a class loader that's an implicit parameter of the entire block of bytecode. What if there is no class loader that knows about both A and B? You can easily compose 2 method handles that come from completely opposite corners of the JVM universe, loaded differently, and then together they come. And many of you, for some reason, still play with class loaders, and then you sometimes create such method handles and try to compose them. Hey, what happens if A and B are spelled the same? Could happen. Has it happened? Anybody? I'll bet it has. And also, there's this funny thing called signature constraints, which nobody understands, which involves additional type crosstalk between types that are mentioned within methods that are called from the same bytecode in signatures. The sum of this is that you have no class def found errors throwing out at you at unpredictable moments. So let me talk a little bit more about off the cliff. As I said, it goes into assembly code and inscrutable to the compiler. The assembly code includes, in order to manage examples like we just saw, if you try to do functional composition in assembly code, you'll have to call f and then push a stack for the continuation of what to do when f returns and you want to call g on its return value. And there's no Java method there. There's just two method handles being executed in sequence. So somehow the JVM needs to keep track of what it's doing. So it needs to push an internal stack frame, which leads to this assembly language stack frame called a ricochet frame, which seemed like a wonderful idea and very clever, but it's gone now. Yeah, okay. Well, we'll give you some other kinds of time sinks in 8. So the fun thing about going off the performance cliff through argument transforms is that you're tooling along in compiled code, your arguments are in registers, you're just all ready to call this method handle, boom, you jump into it, and the method handle says, I have argument transforms, and I only know how to do on-the-fly transforms in the interpreter. So I'll take your register arguments, I'll spill them into a new copy of your argument list that's in the interpreter format. We call that in Hotspot an I to C conversion. C to I conversion, compiled to interpreted. And then I'm going to then execute one snippet at a time the assembly code that performs all the argument transformations you want, including maybe ricochet frames. And all of this is very interpretive in flavor. And then finally, I know that you want to be in compiled mode, and I know your ultimate callee is compiled. So what we'll do is, once we've transformed the arguments, we'll copy them again using something called an I to C converter. And finally, we'll jump really, really fast into the final method. All right, cool. Root problem is too much assembly code and too much entanglement at the wrong level. The VM thinks it knows about each little thing that a method handle needs to do, and it's the wrong level of abstraction. So one thing that's gone in JDK 8 is something called an adapter method handle, which was the worst part of the reference implementation because it was absolutely not understandable unless you really got into this representation of individual argument transforms, which is a waste of time to understand. The problem is that there's the JVM and the JDK, and they both have the burden of understanding in JDK 7 this convention of how to do argument by argument transforms and chains of method handles. And there's a lot of crosstalk between the two big parties saying, how do I swap two arguments? How do I rotate this? How do I do a filter on this argument? How do I unbox this one? Too much detail. So we're representing it differently now. The chain of method handles with the swap argument and cast and uncast and ricochet and so forth, that is the de facto IR that we came up with, just sort of we backed into it during the development of the spec and the initial implementation of 292 in parallel. So we've got a better IR now, and I want to tell you about it. It works at the level, rather than individual argument transformations, at the individual method level. So one block of IR corresponds eventually to a JVM method, but the correspondence is lazy and can be tuned. This obviously meshes better with what the JVM likes to do. Also, it allows the JDK to make lots of detailed representation decisions and then drop one of these method blocks into the VM at a very late date and say, okay, VM, it's time to optimize that. But the executable format does not need to entangle strongly with the JVM. The impact of this refactoring, just to give you the numbers up front, is that the JDK gained, on a churn of 7K lines of code, it gained about half of that in size. So more stuff is up-leveled to the JDK. In the JVM, all the assembly code except for like a one page is gone. And we deleted almost 13,000 lines of code. These are non-comment lines. With a net reduction of almost 8,000 lines of code in the JVM. So the JVM is a lot dumber about JSR 292, which is good, because we tell it simpler things and it can optimize them better. What are the requirements that we were conscious of? Easy to create the IR, easier than bytecodes. Bytecodes are kind of, the ASM tool is wonderful, we use it. But bytecodes are still, you don't want to create a new block of bytecodes every time you make a method handle. Whereas it is plausible, in some cases at least, to create a new IR bundle for every method handle, because it's just a few pasting of pointers together. We want to be able to compose these blocks together and reuse the composed pieces. So they should be designed to be multiple purpose from the start. And we want to be able to reuse them without worrying too much about all the details of Java's static type system and the JVM's verifier. So we make certain loopholes in them that enhance reusability at the expense of safety. That means this is currently a trusted only intermediate representation. And of course it has to be fully competent to do everything that method handles and invokedynamic do. So what does it look like? Well, it's, as I said, similar to Java methods. That means it has arguments and return value. It's not a full emulation of Java methods. That would be kind of redundant. But it is verifiable, and you can render it to bytecodes. Here's the inspiration for it. That's why it's called Lambda Form. Here's a lambda for the composition of two functions. And the scheme version below is intentionally miswritten. Those of you who do scheme will notice it's not tail recursive. There's no tail call at the end. But what you see there is a lambda with three formals, and then two temps, and then one of the names is selected as a return value, and that's the essential form of this new IR. Here's an example to dive straight into details. If you were to permute arguments of a two-argument method handle, here's what the structure might look like. You have MH0, which is the ultimate target, and MH1 is the wrapper, which swaps two arguments. So the first line is what the user would approximately think in terms of the 292 API. The second paragraph is what the new intermediate representation looks like. There's a method handle wrapper around a lambda form, which takes the method handle receiver argument plus the two arguments, and then performs a invocation on the interior ultimate target, MH0, with the swapped arguments. So if you look at this, you'll see lots of line noise, but I think you will agree that it's basically what needs to be done, right? There's sort of a captured value of MH0 in there, and then MH1 is the guy that has the wrapping behavior. Here's the English for that. A linear array of names, first formals and then temporary expressions. That's just a linear structure. Each expression is something called a named function, which is really a symbolic reference, and then a list of an array again of objects. The named function has to be on the boot class path. But that's okay because we have ways of invoking functions from other places using invokers that are on the boot class path. The argument array either contains previous names or arbitrary object constants. And the calls are often weakly typed. There's there's a bootstrapping or a circularity problem. If you want to be able to invoke something, a method handle whose types are off the boot class path, you need some way of avoiding naming those off boot class path types in your call site. And so there's a unchecked primitive called invokeBasic, which does this very nicely. You saw it on the previous slide. I didn't point it out though. The only other thing you have in the Lambda form are an arity, which is actually redundant with the number of non-expressions at the front, and also a return value, which is usually just a reference to the last expression, but it could be a next to last or something like that. There's no naming, there's no symbol table, there's no lookup. It's all small integers. There's even no control flow, no loops, so this is all trivially SSA with no fee nodes. And then for your delectation, I have here the one page of code. This is the actual code of the AST Walker interpreter. So it really does fit on a page of code. And it even has like little features like invocation counters and stuff buried in there. I'm going to come back to this in a sec. The type system for these guys, you saw the funny little colons in there. There's only 5 types. They're basic types. L stands for reference, I stands for int, and so forth. Those of you who are familiar with JVM signatures will recognize these odd letters. But basically you have int, float, long, double, and reference, as I just said. Yeah. And of course you get void if you have a no return. The reason for going to this level of detail is so that everything will be firmly well known to the GC. There's no aliasing of ints and pointers. That would be very bad. But because the pointers are untyped, there is a certain amount of leeway in passing pointers around. So the Lambda forms themselves are responsible for maintaining type safety at the JVM, at the Java level. So they're, in practice, you'll often see casts inside the Lambda forms to make sure that things are the right type before they're handed off to somebody. And if the casts are added, then this renders very, very simply to verifiable bytecodes. So we're all happy there. Let's see, there's no up levels. This is not real lambdas. This is inspired. This is a homage to lambdas. There's no nesting of functions here. A name, if it has an expression, is a simple named function thingy, which which has a symbolic reference but cooks to a method handle, and then a bunch of arguments. Anything else to say? No. Well, I almost slid something by on you. The named function resolves to a method handle, and the method handle in Lambda form interpreter steps through the expressions and calls each named function resolved method handle on the arguments. And so there's a metacircularity there, right? So we have to break it. But it means it's a high leverage design. There's only a few concepts floating around, and they leverage on each other in both directions. The names must be, of course, properly defined. So there's the constructor of the Lambda form asserts that each expression refers to names that are only previously defined. So it steps through them in order. So therefore, the execution of these things is very simple. You allocate a value array when you're given some incoming arguments to a Lambda form. The value array is big enough to hold the incoming actual arguments and also all the temps. And then you walk through the expressions and you evaluate each one and plug them into the value array, and then the value array serves as the sort of table or display or stack frame that gives you the arguments for successive expression evaluations. So it's simple. And then you return whatever you care to return from what you did. So here's that big page code again. To step through it, when you first enter a Lambda form, you make a copy of the incoming arguments, but with resized to be the length of all the names, both formals and expressions. And then you walk through them, starting with the first expression. You don't need to walk through the formals. And you interpret each name in turn and plug its value into the saved values. The interpretation of each name involves another copy of the arguments to that name, which is a little piece of the Lambda form structure. And then for each argument, you look and you see, is it a reference to a previous name? If so, you replace that argument by whatever's in the values array for that name. Otherwise, it's just an untouched constant that was just bound into the Lambda form. And then you call the method handle, and this is where you go metacircular on those arguments with names substituted. And then you come back and eventually return a selected value from your stack frame. The result is a constant small integer on the Lambda form. Usually it refers to the last name in the list. The only reason it's programmable at all is, I might get rid of it, but it is so that it can be less than 0, meaning there's a void return. All right. How do these things run in the actual system? Well, initially, unless there's a bootstrapping reason against it, they're run through the interpreter. This is why, until we put in stack frame filtering, some of you early adopters saw what I think Charlie Nutter called epic backtraces, because there was, like, for one method handle call, there was all these individual Lambda form interpreter frames. And then on the fly and sort of asynchronously with respect to actual execution of method handles, the IR can be transformed and presented to the JVM. It can be, we are currently doing this by rendering to bytecodes. Bytecodes are a fine intermediate representation if you have a moment to build them, and you can sort of spend some time managing them correctly. And the lazy initial execution via interpreter allows you to be lazy enough to sort of manage the bytecodes as cleverly as you like. We use the anonymous classes to load them into the VM. And so you get a mixed mode that goes from the AST interpreter, which is pure Java code, to a bytecode interpreter in the VM, if you have one of those in your VM, to JIT compilation, and that might go through multiple pipeline phases. All right. So how do we put all the pieces together? Well, let me give you some cases. You have to be able to call from a method handle to its internal Lambda form, the Lambda form that provides its behavior. And that's just a jump. The VM knows how to do this. This is a hardwired piece of the system. You have to be able to call the other way from a Lambda form to a method handle. How do you do that? Well, there's a named function called invokeBasic, which is signature polymorphic and non-public. It's this privileged invoker, which as long as you have the right basic types, it will invoke an arbitrary method handle with its Lambda form. How about calling an arbitrary method? Well, in a moment I'll show you the subprimitives for that, but there's a direct method handle is what you use, and it has inside of it a linker that knows how to spin an actual invoke virtual or whatever on a non-constant member reference. And then finally, there's the other way around. Instead of calling from a Lambda form to a Java method, you need to call from Java bytecodes to a method handle. And then we use some adapters in there at a strategic place, which I'll show you in a minute. Okay. Back to the swap arguments example. Let's see, we already did that. No, we didn't do this one yet. Yeah, we did. So here's an example with the, you'll notice that the only temp in this Lambda form is z, which calls the target method handle with the swapped arguments. And you'll notice that the expression binds in as a literal the method handle, which is the target, and this is perfectly reasonable. Here's another example. We're going to return a constant value instead of call another delegate. So the constant value is again bound in as an argument to a handy function, which is an internal identity function that we use. Notice in both cases that the initial method handle argument to the Lambda form is crossed out. By that I mean it's not used. The behavior of both of those two examples is completely dependent upon the bound-in constant. This means that the code of the Lambda form is not reusable across similar use cases. So that leads us to bound method handles, which are in JDK 7 and have been retooled in JDK 8, thanks to Michael Haupt. And so what we have here is a bunch of struct-like classes. We're sort of feeling our way towards doing tuples in the VM. The design here is that it's a depth 1 hierarchy. Each species is final, and they're immutable. And they're manipulated through method handles, so there's more metacircularity there, and generated as needed. So here's the bound method handle example of swap arguments. What we do is oh, are you really going to step through that like that? Okay, sorry. So what we do instead of have the literal constant method handle target, instead we bind it into the body of a method handle struct, and we load it up using an accessor called argl0. Again, non-public and private to the Java Lang invoke package. So here you see is a piece of Lambda form code that is reusable. It can be used for 100 different MH0 values, the same code but different instances of the bound method handle species L. The L, of course, means reference. It's a species that has one reference in it. And you'll notice the MH0 at the very end of the slide, which is where the particular target value is passed into the constructor of the bound method handle. All right, so and constant value is the same kind of a deal. And let's see, that's good. Same story, same species too. One bound pointer value. All right, so now let's go on to direct method handles, which give you a way of calling a Java method or another Java member field or constructor. And these are the guys that directly implement the constant method handle constants that Dan was already talking about. There's an internal VM cookie, which again is privileged, which refers to, in the most direct possible way, a JVM pointer to a method. And we call it member name. And these things are, you compose them as a symbolic reference, then you hand it to the VM and they get resolved, and then the VM can decorate them with whatever internal data structures it needs. So it's sort of a portable separation of concerns API. Direct method handles have Lambda form code which perform any needed checks or conversions, and then there's a weakly typed jump to the member name using a linker intrinsic. For fields we use unsafe, get long and put static and so forth, those sorts of put object. Here are the linkers I'm speaking of. This is the suite of linkers that must be defined as primitives by the JVM. So this is where that page of residual assembly code comes in. The linkers themselves, in order to be able to say, I have a pointer to a non-constant virtual function, and I need to do an invoke virtual on it. And here are the arguments already presented, either interpreted or compiled. What do I do? Is there a vtable? Does this JVM use vtables? Whatever I have to do the virtual call, do it. So there's a bit of assembly code that is able to perform, say, an invoke virtual or an invoke interface on a non-constant name, which is completely different from what the normal interpreter does, since it's working out of nominal bytecodes. So these are those guys, and you'll notice a very peculiar thing, which is that the cookie that says who you're linking to is the trailing argument rather than leading argument. What happened to object orientation? Shouldn't these all be methods on member name? Of course they should be in any right-thinking design. However, the key problem here is that the caller, not the primitive, is responsible for argument shuffling. One major purpose of Lambda forms is argument shuffling. So why design them so that they do argument shuffling, and then you call a linker primitive that has to do more argument shuffling to get the receiver out of the way so that the first argument can really be in RBX or whatever the register is that holds that first argument. So we basically designed this, and this took more weeks than I'd like to say to figure out how to do this, but we designed it to put the disposable argument in a trailing position so that both interpreted and compiled code could conveniently ignore it once it was used. This is a surprisingly important decision in getting off the performance cliff. All right. So here's another example. What if we want to call a hash code? Well, the first thing we have to do is look up and ask the JVM to resolve a cookie that points to object : hash code. I'm using Lambda notation here, obviously. So once I have that cookie, then I make a new I can make a new simple method handle that binds in that cookie as a literal constant. And then I call my linker, link to virtual, to call that guy. And you notice the object is the first argument, and then there's a trailing sort of dropped off member name argument that is ignored as soon as you do the actual call. Here's the real version. We use a direct method handle which has a built-in field called its member name, and that's a parameter to the constructor. And so this Lambda form is, of course, reusable across all members of that same type. In other words, something that takes a reference and returns an int. So any function or method that takes a single reference and returns an int can use this Lambda form body to do its invocation. It has to be a virtual call too. So as I alluded to before, there's a couple points where we're metacircular. Here's the slide that sort of tells it all. The direct method handles are defined in terms of Lambda forms, but those in turn need to be called from the Lambda form interpreter, and likewise with bound method handles. So we manage this by eagerly byte compiling a few Lambda forms that we know have to be used in this way, and the rest can be lazy. All right, the last connection point is with invokedynamic and method handle invoke, the magic invokeExact and invokeGeneric calls. Again, this has been refactored to be much simpler in the JVM. It used to be the JVM knew a lot about what the semantics of these call sites were, and the JVM would manage argument shuffling. Like with invokedynamic, you have to insert the method handle that you're calling into the argument list so that you know who you're invoking. This goes away. This goes out of the VM and into the JDK as follows. There is a linked, when you link one of these call sites, the JDK is asked for a contextual argument, which the JVM links into that call site. The JVM therefore grabs two pieces of information, a behavior pointer, which is a Lambda form, and a trailing argument, which we call the appendix. With invokedynamic, the appendix is the call site instance that's associated with that invokedynamic site. And for method handles, it's the method type which you need to use to check the call. And so the JVM, all the JVM knows is there's a reference, an untyped reference, which it calls the appendix, which Java returns along with a Lambda form. And then to link one of these call sites, it remembers the Lambda form, and that's the behavior at that site. And it also remembers the appendix argument, which is trailed on with the other arguments. I want to emphasize that this linkage decision is not baked into the VM. All the VM knows how to do is make an upcall to Java when it does the first execution of a method handle invoke or an invokedynamic, and the JDK does the rest. The JVM receives back a behavior pointer in the form of a compiled Lambda form, and also an appendix argument, and it's responsible for remembering those two and putting them together whenever the call site's executed. This gives us the ability, for example, to invent new kinds of invoke modes, like invoke partial for binding of bound method handles. And that kind of thing can probably be done, haven't done it yet, but probably be done with little or no additional VM modifications just by JDK code. All right, in the home stretch here, I'm hungry for lunch. Here's an example of invokeExact with an int and a double value. Now that is linked as a call to A with an appendix value called MT. A is a Lambda form that Java creates for this guy who needs it. It could be cached. And it performs the type check that is mandated by JSR 292 at all invokeExact sites. It throws an exception if it needs to. That's the only non-normal, that's the only abrupt exit that a Lambda form can do, is throw an exception, but it's important sometimes. And then it performs the unchecked invoke on the method that's coming in. The JDK also supplies to the JVM the method type value, which is resolved by Java code from the flat symbol that's present at the call site. And here's invokedynamic, same thing, except this time the appendix value is a call site. And so the Lambda form does something that's different in detail, but very similar in spirit. Notice that this Lambda form does not take a method handle as a leading argument. There's nothing about Lambda forms that requires them to take method handles as leading arguments. They're just blocks of code with arguments. And finally, to revisit the functional composition, here is the G of F composer. The same example as before, but the way it's rendered with Lambda forms and bound method handles. Here's a bound method handle species with two references embedded, and it will pick up first one and then the other. The first one is F and the second one is G, and I have a bug in my slide. The last line is wrong. In any case, that should be F and G, not MH0. Okay, in any case, you get it. We pick up the first function, we call it on the incoming argument, we save the value, then we pick up the second function, and we call it on the value and return that result. There are 4 temps there, and you'll notice the expressions are of various kinds. There's one for data structure access, a couple for data structure access, and a couple for delegating to other pieces of behavior elsewhere. What's the status of this work? Well, it's committed to the hotspot comp repository, which means it's sort of it's getting on the train to get up into JDK 8, and we hope to, we're thinking about a backport. The initial feedback from some of you in this room is neutral to positive on performance changes, and thank you for suffering along with us on the early versions of this. It looks like we've beaten the no class def found error. Some performance cliffs have gone away. Tic-tac-toe runs 80% faster for those of you who like to play your tic-tac-toe at speed. But there's more tuning to do, and we think there's a lot of low-hanging fruit. There's various techniques we're thinking about, and it's very nice because a lot of these techniques are completely decoupled from the JVM. It's what you cache and what you record in the JDK, the low-level JDK code that spins Lambda forms. We think that with some additional work, we would be able to, for platforms that require it, statically compute a sort of a basis set of Lambda forms. First, we want to learn how to cache them, then we can learn how to pre-compute them. And it may be that for some cases that turning them from basic blocks into extended basic blocks would be just the right sweet spot for designing this intermediate representation. The idea would be that some expressions would be able to trigger an early return rather than go all the way every time through all of the expressions. So you get a block with multiple normal exits. And we're doing some additional type inference, very light, but the idea is to remove casting where it's really dumb. What we really would like to do is make sure that the final calls out of these guys are tail calls, because they're invisible as stack frames, so there's no reason to keep them around, and they should be tail calling each other. In any good system, well, in any scheme system, they would be they'd be tail calls, or Haskell. So I think when we get some of this stuff rolling, we'll be able to use these Lambda forms for other things besides method handles. In fact, we should use them for FIDOs, and that's my contribution today to the nomenclature of the industry. A FIDO, of course, is a functional interface delegate object, which don't think too hard about what those words mean. It's a really great acronym, though. So that's that's what I have to tell you about the implementation work. It's almost like you do a new processor architecture, and then for the next, that's a tick, and then for the next release you do a talk, which is a sort of a process shrink and performance improvement. So although there's a lot of different stuff down in the details here, for users hopefully it's just a process shrink and a performance improvement.